Fantastic. So we're really delighted to have David back for the second part of his talk on singular Lagrangians and constrained Hamiltonian systems. If you were not here last week, just a brief bio. So David received his PhD in physics from the University of Texas at Austin, working with Claudio Bunster and Marc Henneaux. He then held postdoctoral positions at the University of Vienna, the University of Texas at Austin, and the University of North Carolina, where he worked closely with James York. Since then, David has been a professor in the Department of Physics at North Carolina State University, and in 2010 was elected Fellow of the American Physical Society. David's research has spanned a number of topics in general relativity and quantum gravity, including black hole thermodynamics and numerical relativity, with current interests including the extreme mass ratio in-spiral problem, which is to say predicting the motion of a small black hole or neutron stars as spirals into a large black hole. And David is the creator of the YouTube channel Physics Unsimplified, which includes lectures on general relativity and various topics in classical mechanics. And he recently authored an undergraduate textbook, Introduction to Scientific Computation, which is to be published soon by World Scientific. So thank you all for joining. Thank you, David, for coming in and taking the time, especially early in the morning. And I know you haven't been well, so thank you very much for powering through for us. And we're ready to hear your talk. Please take it away.
Okay. Yes. Thank you. Yeah, it's a pleasure to be here, and it is early, but I can promise myself a nap later on, so that'll be fine. So I want to jump in and just pick up where I left off last time with the story of dealing with singular Lagrangians and constrained Hamiltonian systems. So let's see here. So let me remind you what I mean by a singular Lagrangian system is one in which the mass matrix, this second derivative of the Lagrangian with respect to the velocities, the q dots, this matrix is singular. And this has a number of consequences. First of all, when this is singular, that means we can't invert this matrix, and we can't solve Lagrange's equations for all of the accelerations. Another further consequence is that we can't solve these definitions of the conjugate momenta, partial L with respect to the velocities. We can't solve these equations for all of the q dots, all of the velocities. And finally, as I discussed last time, all this implies that the system is constrained. There are constraints on the variables. So converting a system like this into Hamiltonian form is a little bit less trivial. It's quite a bit less trivial than for a non-singular system. And we have to use what's called the Dirac-Bergmann algorithm. Okay, so what I want to do is, similar to last time, I want to explain a lot of what's going on just by way of example. So let me start with a fun singular example. This is I just call sort of unimaginatively the pendulum and two springs. So we have two springs here attached to the ceiling, one at minus d, one at plus d, so a distance 2d apart. And the springs are attached together at this point where there's also the pendulum rod is attached. And then this is the mass, m, is down here. This is the pendulum bob. We'll take the stiffness of the spring or the spring constant to be k. And just for simplicity, I'll take the relaxed length of each spring to be 0. You can let it be non-zero, but then the algebra becomes a lot more messy. The length of the pendulum is little l. And for dynamical variables, for the generalized coordinates for this system, we'll use the xy coordinates of this point of attachment and also the angle theta between the pendulum rod and the vertical. Okay, so we need to build the Lagrangian for this system in terms of x, y, and theta. So first of all, we need to know the Cartesian coordinates of this pendulum bob, and I call that capital X and capital Y. So capital X is just little x plus L sine theta. Capital Y is little y minus L cosine theta. And we can differentiate these relationships in time, and x dot is little x dot plus L cosine theta, theta dot. Similar expression for y dot. And from here, we can build the kinetic energy, T, is just 1/2 mv squared for the pendulum bob. So v squared is x dot squared plus y dot squared. And when you put in these expressions to write it in terms of the generalized coordinates, we have all of this for the kinetic energy. And for the potential energy, it's just the gravitational potential energy of the pendulum bob, mg capital Y, and that becomes this term. And we also have the potential energy in the springs. So this is the potential energy in, I guess, the spring on the left or the spring on the right. Well, one of the two, okay? One of them, so what's in square brackets here is the square of the length of the spring. And likewise for the other spring, this is the square of the length of the spring. So these are just the potential energy terms for these two springs, and they simplify a bit down to this expression. Okay, so as usual, the Lagrangian is T minus V, kinetic minus potential energy. So let's see, the top line here is kinetic energy. The bottom line is the negative of the potential energy. And now we compute the mass matrix, second derivative of L with respect to the velocities. And this is the mass matrix. And I don't know if you can compute determinants in your head very quickly, but it turns out that the determinant of this matrix is 0. So that means it can't be inverted. We can't solve for the accelerations. The Lagrangian is singular. Okay, so let's now construct the Hamiltonian version of this theory. We need to employ the Dirac-Bergmann algorithm. Okay, the first step, and I've numbered these steps like I numbered them last time. Step number 1 is to compute the conjugate momenta. So this is the momentum conjugate to x, y, and theta. So this is, well, I didn't put the definitions, but p sub x is just partial of Lagrangian with respect to x dot. You get this expression and so forth. So these are the conjugate momenta. And we know from the general theory that we can't solve these equations for theta dots, x dot, y dot, and theta dot in terms of the p's and q's. And furthermore, there are constraints implied by these definitions. All right, and there's procedures to find the constraints, but really just fool around a little bit with these equations, and you'll find this is the constraint, minus LPX cosine theta minus LPY sine theta plus P theta. So if you use these definitions of the P's in this expression, you'll find it's identically equal to 0. Again, I'm having to do this with the mouse, so it's kind of hard to draw. Okay, so this is referred to as a primary constraint because it's a constraint that comes about just due to the definitions of the conjugate momenta. Okay, the third step in this algorithm is to construct the canonical Hamiltonian, and it's constructed in just the way the Hamiltonian is usually constructed. Px dot plus px x dot plus py y dot plus p theta theta dot minus the Lagrangian. And even though we can't invert these relations for the velocities in terms of the coordinates and momenta, it's still true that you can write this expression in terms of just coordinates and momenta. And this is the result that you get. There's something I believe I forgot to mention or emphasize last time in the last lecture is the canonical Hamiltonian is not unique. You can write it in lots of different ways. For example, we could take this equation, this constraint, which of course is equal to 0. We could, for example, solve this for p sub x in terms of p sub y theta and p sub theta and plug it into here. And we would have a different form of the canonical Hamiltonian. But part of the, what is, if you go through the logic step by step, that's part of the reasoning is to show that it doesn't matter how you write this canonical Hamiltonian. It doesn't matter how you write it in terms of mixing up the variables by using this constraint. The algorithm works itself out anyway. But this just happened to be, I think, the simplest, prettiest way to write the canonical Hamiltonian, for this example at least. Okay, so the next step in the algorithm is to define what's called the primary Hamiltonian, and it's just the canonical Hamiltonian plus Lagrange multipliers times these primary constraints. So here's the, is that correct? Yes, this was the canonical Hamiltonian in the first line here. Here's, in the second line is the Lagrange multiplier times the primary constraint. All right, the next step is we must apply consistency conditions. In other words, we have to ensure that the constraints, the primary constraints, are preserved in time under the Hamiltonian evolution. So this is the Poisson bracket of the primary constraint with the primary Hamiltonian. So this is the time derivative of phi. And for this example, when you compute that, what you get is 2kl times x cosine theta plus y sine theta. So we need to set that equal to 0 in order to ensure that phi is preserved, phi equals 0 is preserved in time. This must equal 0. So this is what's referred to as a secondary constraint, and we'll denote that by psi. By the way, so this is the secondary constraint, psi is equal to 0. This is, you might say, well, why don't we just drop the factor of 2kl? After all, if psi is equal to 0, then this quantity in parentheses must equal 0. And that's true. There are many ways you can write this constraint. All right, we could write this constraint as, I don't know, y, what is it? Y divided by x equals, or plus y over x plus arc tangent of theta is equal to 0, for example. And again, that's part in the details of the logic of the Dirac-Bergmann algorithm. You can argue that it doesn't matter how you write this constraint, the whole thing works out in the end anyway. Now, actually, I should probably make a further comment about that. I say that it doesn't matter how you write this constraint. There are many different equivalent ways of writing this constraint, and as well as the primary constraint. But it's not entirely true that you're completely free to write the constraints any way you like. So for example, I could write this constraint as, I could take the quantity in parentheses x cosine theta plus y sine theta and raise it to, I don't know, the 10th power. All right, that wouldn't be a good way to write the constraint because, and basically what you want is you want to write the constraint in such a way that, loosely speaking, the gradient of the constraint needs to be non-zero. So in other words, you need to write the constraint as a function that actually, away from the 0 value, this function on phase space is actually, positive on one side and negative on the other side of this surface. All right, if I raise this to the 10th power, then the gradient wouldn't be 0, right? You can imagine differentiating psi with respect to some of these variables. And what you would have is this quantity in parentheses to the 9th power, but that's 0. So the gradient would be 0 in that case. So that's sort of roughly speaking the way I think about it, that you need to write the constraints in a way that these functions have non-zero gradients.
And this is related to the procedure of extremization with Lagrange multipliers, that you need always that gradient to be non-zero.
These gradients are
that-
the forces. They're the constraint forces, essentially. The gradients are the forces that pull you in. And if those are 0, the constraint doesn't do its job.
Yes, that must be the same thing. I have to confess, I never really thought about it in the case of ordinary, so to speak, constraints in Lagrangian formalism, ordinary holonomic constraints, but that must be true as well, that you want the gradients to be non-zero. Otherwise, well, I think the general statement is that the Lagrange multiplier is proportional to the force of constraint. And you'd probably run into a condition where the Lagrange multiplier is 0 times the force of constraint, or 1 over 0, or something like that.
Right.
So yeah, you probably need to have a condition like that in that context as well. Okay, so that's applying the consistency condition on phi. We need to have this quantity psi equal to 0. And now we continue to check that psi is preserved in time. So Poisson bracket of psi with the primary Hamiltonian. When you compute it, you find this expression, which involves the Lagrange multiplier lambda. And this can be solved for lambda. So this is what we refer to as a restriction on the Lagrange multiplier. So it doesn't imply any further constraints on the phase space variables, but it does restrict the Lagrange multiplier. Now, sorry, things shifted there a bit. So this is the expression again for the Lagrange multiplier. There's a subtlety in this example that comes about because looking at the denominator here, you might worry that it becomes 0 at some point. And it turns out that as you can show that as long as you demand that this mass stay below the ceiling, the level of the ceiling, the denominator is always positive. So that's not a problem, just with that condition. And this is, I think, probably part of another subtlety in this whole algorithm. And the subtlety actually begins from step 1. We assume that in step 1 that the Lagrangian is singular and you can't invert the definitions of the momenta for the velocities. And that mass matrix has a certain rank. In this example, it's a rank 2 matrix. And so that means, there's sort of, if you diagonalized it, there's sort of 1, 0 in the mass matrix, which means there's one primary constraint. And there's an assumption in this business that mass matrix has a constant rank. Okay, and it's not necessarily always true. There could be different regions of phase space where the rank of the matrix changes. And I think that something like that is going on here. You could probably describe it in those terms. If the mass is right at the level of the ceiling, then you can show that this denominator degenerates to 0, and the whole procedure sort of falls apart. Or it actually, I think it goes into a different regime where it's more like a first-class constraint. After all, if you look at this condition, this consistency condition, you'll see whenever this coefficient in parenthesis is 0, this is no longer putting a restriction on the Lagrange multiplier. Okay. Instead, this is putting another condition on the P's and the Q's. So the whole problem kind of changes character in that case. So we're not going to worry about that. We'll just assume the mass stays below the ceiling, the denominator stays non-zero. So we're just working in one region of phase space. All right, the next step in the Dirac-Bergmann algorithm is to construct what's called the total Hamiltonian, and that's obtained from the primary Hamiltonian by inserting the restrictions on Lagrange multipliers. So here's that expression for the Lagrange multiplier. This is the primary constraint, and this is the rest of, actually the first line is just the canonical Hamiltonian. Okay. Next step, we want to separate the constraints into first and second class. We have two constraints, phi and psi. First class constraints, if you'll remember, are constraints that have vanishing Poisson brackets with all of the other constraints. And by vanishing, I mean vanishing when the constraints hold. And then in this case, if you compute the Poisson bracket of phi with psi, you get something that's not 0. Okay, actually, you get this same expression here that we're assuming because the mass stays below the ceiling. We're assuming that's non-zero. All right, so that means that phi, the bracket of phi with psi is non-zero, so phi is not first class. The bracket of psi with phi is non-zero, so psi is not first class. They're both second class constraints. In this example, it's like the example I went through in the last lecture. There are no first class constraints in this example. Okay, so the next step is to construct the Dirac bracket. So we collect the constraints, the second class constraints, that's the SC here, into a set with this index mu just ranges over 1 and 2 for the two constraints. All right, this matrix of Poisson brackets of the second class constraints with one another, I call M. And then the Dirac bracket with the star is constructed from the Poisson brackets without the star in this way, where this M inverse is the inverse of this matrix. For this example, and you know, I do all this in Mathematica these days because these calculations get a little bit messy. The fundamental Poisson brackets, meaning the Poisson brackets, sorry, Dirac brackets, the fundamental ones, meaning the brackets between the phase space variables. We have a bunch of non-zero ones. Bracket of x with p sub x is this expression, 1 minus a bunch of messy stuff. Y with p sub y, theta with p sub theta. These are interesting because if you know, if you're used to doing Hamiltonian mechanics with this Poisson bracket notation, you'll know very well that the Poisson bracket of x with p sub x is just 1. Poisson bracket of any generalized coordinate with its conjugate is always 1. And here we see for the Dirac brackets, that's not true. And in fact, there's a bunch of other brackets that were non-zero. I just listed them here. Unlike the Poisson bracket, where a variable, a coordinate with a conjugate of a different coordinate is always 0, here it's not 0. So we have this set of fundamental Dirac brackets. And now, if we agree with ourselves to use the Dirac bracket from now on, we're free to eliminate variables however we like using the constraints, using the second class constraints. So here are the second class constraints again, and we can solve these to eliminate some of the variables. The most, I think the natural ones to use here are to solve this equation for p sub theta and to solve the second equation psi equals 0 for theta itself. And we can eliminate theta and p sub theta. And I should emphasize there's no rule that says you have to eliminate, you know, if you eliminate some generalized coordinate, you have to eliminate its conjugate. Okay, I could eliminate theta and p sub y, or x and theta if I like. But again, it just, I think, makes the algebra turn out a little bit cleaner to make this choice. Okay, so then you reduce the Hamiltonian by, and reducing it really just means simplifying it if you can, by using these expressions in place of theta and p sub theta. Okay, so when you do that, let's go back here to the, I don't know where the, here's the total Hamiltonian. I'm just inserting those expressions for theta and p sub theta into this total Hamiltonian. Okay, and what you get is this reduced form of the Hamiltonian, which looks like this. All right, so now we can easily write down the Hamilton's equations, the equations of motion, x dot, y dot, px dot, py dot. And when I say easily, I mean Mathematica can do it easily. Yeah, so these are the results for this system. And now we have it in nice Hamiltonian form. We can freely give initial data, x, y, px, and py, solve these equations numerically if we have to, and that's what I'll show you in a minute. And if we want to reproduce or find out what happens to theta and p sub theta as functions of time, we can just plug into these expressions, right? If we know x, y, px, and py as functions of time, we just plug in here to obtain theta and p sub theta as functions of time. So actually, let's see. Yeah, let me go ahead and show you this simulation. See if I can.
I'm sorry. So what happens? So you plug in initial data to solve these equations of motion. So what happens if you plug in something unphysical for, you know, x? You said x needs to be below the ceiling. Is it sort of built into these equations of motion that it breaks?
So if we started with y above the ceiling, for example,
Yeah, sorry,
Uh, well, that's an interesting question. I don't, it doesn't look like here, it doesn't look like anything breaks. It may be one of those situations where the singularities sort of cancel out by the time you get this far down the road, and maybe this is the same equations, whether it's above or below ceiling. I actually don't know uh, what happens.
Okay, cool. Yeah.
But there's nothing else I mean, we're free to give x, y, px, and py at the initial time. We're free to give those freely. What we could do is we could also write down the equations for theta dot and p sub theta dot, okay, and evolve those. In fact, I think the way I've written this code, I think I probably did it that way. Instead of what I described here, solving these equations numerically and then substituting in here to find theta and p sub theta, I just evolved them all at once. So we also have, the Dirac bracket and reduced Hamiltonian are happy to also compute the time derivatives of theta and p sub theta. But when you assign initial data for theta and p sub theta, along with the x's, y's, px's, py, they have to satisfy the constraints.
Okay.
Okay, so in fact, so here's the code. Yes, so you can see here I have no, I guess I did just define, I'm probably only defining x, y, px, and py dot. It's actually been a while since I wrote this code. Yes, and as I go through this loop, this is the time step. I'm just computing theta from its expression in terms of x, y, px, and py. Yeah, okay. At any rate, let me just show you the visualization, the movie, because it's kind of fun. So this is the system. Okay. So that's what that looks like. Evolving using these equations of motion with the Dirac bracket and the reduced Hamiltonian.
Out of curiosity, is this a chaotic system, like a double pendulum? Or do you not, or is it hard to tell it's chaotic?
Well, good question. I don't think it's chaotic. Let's see, is there any reason, any simple way you can see? Yes, I don't know. I haven't thought about it, and I haven't. Well, that little movie was made with a pretty crude code, so it would be, I'd have to write the code with a much more accurate, time solver to actually investigate chaos. Yes, I don't know.
Maybe along the same lines. So this is a beautiful algorithm. We get this incredible set of equations, and the motion is beautiful. But it's the price we pay, I think, is that it's a little hard to analyze these equations. What I was thinking about was, there's sort of eigenmodes of the system where maybe it just goes up and down, for example, simple motion. And it seems like it'd be difficult to extract that from these equations.
It's not terribly linear, right? If you
Yeah.
right inside here.
Yeah, I agree. I mean, it's probably easier to go back to the Lagrange's equations and just work from there, work out the eigenmodes and so forth. Yeah, I often find myself thinking about this algorithm in those terms, like, is this worth it? right? I mean, it's really beautiful and fun, but in a practical sense, it's just a lot of work and a lot of little details to learn. And yeah, you could, with a little bit of physical insight, you can go back to the Lagrange's equations and sort of see what's going on. Um, so what's going on is the angle theta of the pendulum rod is not independent of the XY coordinates of the point of attachment. Because if you think about the pendulum rod is sort of pulling on those springs and the forces and the springs are, so imagine that the point of attachment as being a little massless point, right? It has forces on it from the springs and forces on it and a force on it from the pendulum rod. And those forces have to be balanced, right? Because there's no mass there. So it can't have an unbalanced force, or there would be infinite acceleration. So that's all that's going on there physically. And so you could kind of work that into your analysis and probably go from there and never need to employ all this Dirac Bergmann algorithm.
I think
It's,
the
it's
point
still
is-
fun to see it in a simple example.
Yeah, but I think it seems like what you've done here is sort of one of the ways one deals with holonomic constraints, where you solve for some of the coordinates in terms of the others, and then just do your usual say variation of the action. And then the sort of the other way that you could go with the Lagrangian method is employing the Lagrange multipliers, and then you get the advantage of learning about the constraint forces. And I think in a way that I don't fully appreciate or understand, in gauge theories, when you want to keep things more flexible and basically have a Lagrange multiplier version of fixing the gauge, this Dirac-Bergmann algorithm is really important.
Yeah, I think even if, like, you read the Henneaux and Teitelboim book, I mean, they would say the same thing. It's the benefit is the insights, is sort of the insights you get. It's not necessarily beneficial for practical calculations, but you do get further insights into what's going on in the system by keeping that flexibility.
Right.
Just like you do with holonomic constraints, keeping them in with the Lagrange multiplier, you get more out of it because you learn about the forces of constraint and so forth.
Right.
On your point, I think in a gauge system, there's like this additional constraint that you're adding that's coming from you choosing the gauge,
Right.
and fixing the gauge. Whereas here, the constraints are coming from inherently the fact that the mass matrix is not singular. So I don't know if these are the same types of constraints that we're conflating.
They are. I'm about to show you an example.
Great.
That's good. We will pay Ben a little later for setting up perfectly.
Yes, perfect, yes. Okay, so so this is just a summary of the first steps in the algorithm. We compute conjugate momenta, we identify primary constraints, the phi's, construct the canonical Hamiltonian, which is this expression, but written in terms of the P's and Q's. That's why I put it in quotes here. We define the primary Hamiltonian this way. We apply consistency conditions to identify secondary, maybe tertiary constraints, which I'm denoted here by psi. And there's also can be restrictions on the Lagrange multipliers coming from this. The next step is to construct the total Hamiltonian, which is obtained from the primary Hamiltonian by putting in the restrictions on the Lagrange multipliers. And then the next step is to separate the constraints into first class and second class. So we take all of these primary, secondary, tertiary constraints, package them together, and then separate them again into first class and second class. The first class constraints have vanishing Poisson brackets with all of the other constraints. And the second class constraints are just the ones that aren't first class. Okay, so as we've seen in these examples, if there are no first class constraints, which is all the example I gave in the last lecture and this one I just finished, were examples where there are no first class constraints. They were all second class. So we just constructed the Dirac bracket, the bracket with the star, and then we reduced the Hamiltonian and wrote the equations of motion as with the Dirac bracket and the reduced Hamiltonian. Okay, but if, now this is the same 7 steps, but if there are first-class constraints, what do we do? Well, there's some subtleties here that aren't really, you can't really see from these simple examples, but one subtlety is that, well, first of all, if there are first-class constraints, then the Lagrange multipliers aren't completely determined. And it can be a little complicated because what can happen is you can have some equations that determine some of the Lagrange multipliers, but they may be determined in terms of not only the P's and Q's, but other Lagrange multipliers. So the whole thing can, all those terms in the Hamiltonian can get kind of mixed up. But it turns out that this total Hamiltonian can always be split into this form, okay, where you have what's called the first class Hamiltonian, and then you have a bunch of Lagrange multipliers times constraints. And these constraints, PFC, this stands for primary first class. So these constraints are built from the primary first class constraints. They may be certain linear combinations of them, but these are all coming from the first class constraints that are primary first class constraints. And then you have some arbitrary multipliers, which again may be some of the original lambdas, or they may be some combination of lambdas. Okay, so we have, at this point, we have the total Hamiltonian. It's the same total Hamiltonian as up here, but it can be shown that it can be written in this way in terms of first class Hamiltonian. And by the way, this is called first class because you can show that this has vanishing Poisson brackets with all of the first class constraints. Okay, so
Sorry, you pause there for a moment. Is it obvious that that first class Hamiltonian has vanishing Poisson brackets with first class constraints?
um, I think so. No, I'm sorry, I don't remember the argument. I do remember reading there's a paragraph in one of those papers that I wrote where I said, well, we could compute in an example, we could compute the Poisson brackets of this with the first class constraints and show that it vanishes, but it's not necessary because it's obvious because of such and such reasoning.
I guess
So,
the primary
I-
Hamiltonian is going to have vanishing Poisson brackets with any of the constraints. And then you're just restricting the lambdas on
Yes.
per
Yes,
constraint.
because of the consistency conditions, you know that the Poisson brackets of, I think that's right, the Poisson brackets of HT with any of the first class constraints vanish.
Yeah,
And because these are built from first class constraints, you know their Poisson brackets with the first class constraints vanish. And
Right.
so this must vanish also. I think that's roughly the argument.
okay. Very
Poisson
good. Thank
bracket of this with first class constraints vanish.
Great.
Right. So these primary first class constraints, these are the first class constraints that were primary constraints as well. These play an important role because these are the generators of gauge transformations. And we can write the gauge transformations in this way. Okay, so Poisson bracket of any phase space function, in particular the Q's and P's, with this as a generator. This is a gauge transformation. So in other words, this transformation of the phase space variables is not changing the physical state of the system. Okay, and we can also see this by just the role that the primary first class constraints play by writing out Hamilton's equations, right? So this is Poisson brackets with the total Hamiltonian, and we use the splitting of the total Hamiltonian into first class and these lambdas times the primary first class constraints. And you can see here that these equations of motion have these arbitrary functions, these lambda a's. These are arbitrary functions of time in them. So this system, a system like this, actually doesn't uniquely determine the q's and p's as functions of time. They're arbitrary functions in the solutions. Okay, so the primary first-class constraints generate these transformations, which are gauge transformations. But here's the tricky part. Not all gauge transformations are necessarily generated by primary first-class constraints. So the system can have other gauge symmetries besides those that are generated by the primary first-class constraints. Okay, we know this from examples. And the Dirac conjecture, what's known as the Dirac conjecture, is that all first-class constraints generate gauge transformations. Okay, now so not just the primary first-class constraints, but all first-class constraints. So turns out this is kind of interesting conjecture because there's been lots and lots of papers written on this over the years. It's known that in some sense this conjecture is not true because people have devised counterexamples to this conjecture, but it still seems to be close to being true in some sense, that you would want to say that for any reasonable physical system, it's probably true. So it's one of those things. It's hard to find exactly what condition you might need to put on the theory for this to be true. I'll comment more about this later. And actually, this is the simple example I'm about to show you. This doesn't come up because there aren't any first-class constraints that aren't primary. So you have to get to a pretty complicated example to see the Dirac conjecture coming into play. But I'll comment on this more in a bit. Okay, so here's the first 7 steps again. And if there are first-class constraints, what do we do? If there are first-class constraints, then the next step after separating the constraints into first and second class, the next step is to define, or this would be Dirac's recommendation, define what's called the extended Hamiltonian, in which we take the first class Hamiltonian and so this is just the same expression that we had before for the total Hamiltonian, except instead of only the primary first class constraints here, we have all of the first class constraints. Okay, so again, this interesting subtlety here because it doesn't come up in practice very much because you have to have a fairly complicated example where there are first-class constraints that aren't primary. But strictly speaking, what's happening here is you're going beyond what's sort of contained in the original Lagrangian theory, but you're going beyond it in a way that can make sense. So, like I said, I'll try to come back to this point later. Now, the next step in dealing with first-class constraints, systems that have first-class constraints, there's really a couple of choices here. One choice is that we can decide that we want to leave the gauge freedom of the theory intact. We don't want to destroy it. We want to keep it in the theory. So what we do is just proceed as if there weren't any first-class constraints. We construct the Dirac bracket using second-class constraints the same way we did in those examples. And then if we like, we can use the second-class constraints to eliminate variables and obtain a reduced Hamiltonian. And I would call it, in this case, a partially reduced Hamiltonian because there's still gauge freedom and first-class constraints floating around. So that's one choice. And a second choice that we have after constructing the extended Hamiltonian is to eliminate the gauge freedom. Okay, and if we decide to eliminate the gauge freedom, we would proceed as follows. We would choose gauge conditions, okay? So choose gauge conditions such that the gauge conditions along with the first class constraints together become second class. Okay, now we have, extended set of constraints. The first class constraints, the gauge conditions, as well as any second class constraints that might be left over or that might have arisen from the beginning. And we can construct a Dirac bracket using all of those constraints, the second class constraints, the first class constraints, and the gauge conditions, because as a group, they're all second class now. Okay, and then we can eliminate variables as we like. We can use the constraints to simplify things and eliminate variables. And if we like, reduce the Hamiltonian to a fully reduced one in which all the constraints have been taken into account. Okay, so as I mentioned, you have to get to a fairly complicated example to see a lot of these intricacies coming into play. This paper, I know this sounds like an advertisement, but this paper that I wrote that's in Universe is the only I invented this example just to have an example that touches on all these subtleties. And this is the Lagrangian for the example. There are 4 generalized coordinates, and it's pretty contrived. So I have no idea what sort of dynamical system this might correspond to, but it's just a Lagrangian that you can analyze with the Dirac-Bergmann algorithm. And it has primary and secondary constraints. It has restrictions on the Lagrange multipliers. Some of the constraints are first class, some are second class, so it has gauge freedom, and you can consider whether or not you want to include the secondary first class constraints in with the primary first class constraints and consider them to be generators of gauge freedom and so forth. I will say briefly that the insight that you get from this example into the Dirac conjecture is that at this Lagrangian level, the gauge freedom is such that the gauge transformation on these Qs involves an arbitrary function, as you would expect from any gauge symmetry, gauge invariance. But it depends on that function in such a way that some of the variables just depend on the function itself, and others depend on not only the function, but also the integral of the function over time. In fact, you could always change that function to be a total derivative, and it's probably easier to think about it as the variation, the gauge transformation on these variables. Some of them involve, I don't know, some of them involve some function, say f, some arbitrary function, or let me call it capital lambda. Okay, and other variables, that's another delta Q, different Qs involve derivatives, time derivatives of the arbitrary function. So what happens in this case is that you can argue, and I've talked about this in this paper, you can argue that there's enough freedom in this function that, in a sense, it's just the same sense that a function and the derivative of a function at any given point, these are functions of time. So at any given time, the value of the function and the derivative of the function are independent. You can make them, the value of the function and its derivative can be anything you like. Okay, and it's in that sense that you have this gauge freedom, which is represented by a single function. It's really sort of 2 gauge freedoms because of the independence of the function and its time derivative. And that's what's happening with the Dirac conjecture, is that by subscribing to the Dirac conjecture and including the secondary first class constraints, you're just splitting this gauge invariance off to make it explicit that this Q, whichever Q this is delta Q, this can be varied independently of this Q because of the independence of lambda and lambda dot. So there's something like that going on, and I don't claim to have a perfect understanding of it, but there's some insights, as I say in this paper, into the Dirac conjecture. All right, so let me get to an example now. And as I say, this example it doesn't show all of the subtleties, but it's fun. Okay, so and still shows some of them. So this is I just call masses, rods, and springs. So we have 4 masses, these red balls, and they're attached at the midpoints of these sort of greenish rods, and these rods are extensible, meaning they're like curtain rods that are sort of tubes that slide in and out of each other, so the lengths can change as needed. Okay, and the corners of these extensible rods, the green rods, slide along these vertical posts, and then there are springs attached to between the masses and the ceiling. So for generalized coordinates for this system, we use y1, y2, y3, and y4. That's the height of the corners above the floor. All right, so that's the system. Actually, let me go ahead and show you. I want to go ahead and show you a simulation. So this is what it looks like. Okay, I might show it again in a bit as I explain some of what's going on, but it looks like, at least to me, it looks like just an ordinary dynamical system. But it's actually a gauge theory, sort of in disguise. So let's construct the Lagrangian. So the masses sit at the midpoints of those extensible rods. So the height of the mass that's between the corner number 1 and corner number 2, that the height of that mass is y1 plus y2 over 2, and this is the time derivative of that. So this is the kinetic energy, a term for each of the 4 masses. This is the gravitational potential energy. If you work it out, it just simplifies to this expression. And then this is the potential energy in each of the 4 springs, these 4 terms. We have the spring stiffness K. This constant A is just a constant. It comes from the relaxed length of the springs and the height of the ceiling. It's some combination of those constants. So this is the Lagrangian, T minus V. First step in the algorithm, we define the conjugate momenta. So these are derivatives with respect of the Lagrangian with respect to the velocities, y1 dot, y2 dot, and so forth. You can show that you can compute the second derivatives and show that the mass matrix is singular. And it has rank 3, which means there's 1 primary constraint. And again, it just doesn't take you don't have to be too fancy about figuring out what the constraint is. If you just fool around with these definitions, you find that this is the one and only primary constraint. Okay, so here's the next step. Step 3 is the canonical Hamiltonian. Again, Mathematica is very helpful here. So we write, PQ dot minus L and write that in terms of the P's and the Q's. So this is the canonical Hamiltonian. The primary Hamiltonian is just this canonical Hamiltonian plus a Lagrange multiplier times that primary constraint. Okay, now we apply the consistency conditions to ensure that the primary constraint is preserved in time. And I wrote out a little bit of the calculation here. This is the primary constraint. And we're taking the Poisson bracket of that with the primary Hamiltonian. Now the primary Hamiltonian, and these are Poisson brackets. So if you recall that the only non-zero Poisson brackets with a momentum variable is the corresponding coordinate, right? So all of the momentum terms in HP aren't going to contribute to the bracket, to the Poisson bracket. So here's again the constraint. The only terms that contribute are these potential energy terms. This is the gravitational potential energy term. And that actually doesn't give anything because P1 bracket with Y1 is -1. P2 bracket with Y2 is -2, but there's a minus sign here, so those terms cancel. And likewise, P3 with Y3, P4 with Y4, they just give plus and minus ones in combinations that cancel to give 0. And it's also true that the Poisson brackets of this constraint with the spring potential energy terms, they all vanish. So, for example, if you look at the Poisson bracket between P1 and P2 and this Y1 plus Y2 term, well, the Poisson bracket is the same apart from the minus sign, basically because Y1 and Y2 play symmetric roles here. P1 and P2 play symmetric roles apart from the minus sign. So when you take that Poisson bracket, you just get 0. So everything cancels, and this is equal to 0. So that's the consistency condition, and this is the place where we, if this had been non-zero, we would have had secondary constraints, or maybe restrictions on Lagrange multipliers, but there aren't any because this is just 0 anyway. So there are no secondary constraints in this example, and no restrictions on the Lagrange multipliers. And the total Hamiltonian, remember, is obtained from the primary Hamiltonian by inserting restrictions on the Lagrange multipliers. There aren't any, so the total Hamiltonian is just the same as the primary Hamiltonian. Okay, the next step is to classify the constraints as first and second class. There's only one constraint, it's the phi, and the Poisson bracket of anything with itself is always 0 because the Poisson bracket is antisymmetric. So that means phi is first class. Okay, so since phi is a primary first class constraint, it generates a gauge freedom. So oftentimes we throw in a factor of epsilon and some function of time and call this the gauge generator. So this phi generates a gauge transformation just through the Poisson bracket. And if you work it out, this is what the gauge transformation looks like. The transformation of Y1 is just epsilon, Y2 is minus epsilon, and so forth. A gauge transformation on any of the P's just is 0. So just a bit of terminology here. Oftentimes people refer to observables as gauge invariant functions. In other words, they're things that don't change under gauge transformation. And in this example, observables would include the locations of the masses. So remember, the masses are located halfway between the corners of that contraption. The height of the corners were Y1 and Y2 for the first two corners divided by 2. It would be the average, would be where that mass is between corner 1 and corner 2. This combination is an observable. It's gauge invariant. And you can see from here that the gauge transformation on Y1 plus Y2 is 0, just because these come in with opposite signs. And just to emphasize, gauge transformations are, again, transformations that don't change the state of the system. So let me show you, let me go back to the, let's see. What I did here is I just modified my simulation of this system to show the gauge freedom. Okay, this doesn't always play nice with the web browser, so let me try this again. Here we go. So what's happening here, you can see this is just evolving through a series of different gauge, just transforming the variables with that gauge transformation in a sinusoidal fashion. And you can see here what's happening is these extensible rods are wiggling, but the masses themselves are staying put. So the masses aren't moving, the springs aren't stretching or compressing. So nothing about this system physically, because after all, I mean, you know, again, these rods are unphysical, right? They're massless, idealized rods. So nothing that's a physical part of the system, namely the masses and springs, is changing, but I'm changing the dynamical variables by toggling the y values of the corners. Say, I'm toggling them in this way. Okay, so that's why the system has gauge freedom. Even though it naturally wants to be, I think the most natural set of generalized coordinates for this system are these y's. And after all, there are 4 rods, there are 4 masses, so it's natural to want to use 4 generalized coordinates. But the generalized coordinates are not actually independent in this case. And there's this gauge freedom that allows those extensible rods that run through the masses to wiggle back and forth without changing the masses themselves, changing their positions or the lengths of the springs. Okay, so that's why this system is a gauge theory. And the next step in the Dirac-Bergmann algorithm, since we're dealing with a theory with first-class constraints, is to write down the extended Hamiltonian, in which we would include the secondary or tertiary first-class constraints, but there aren't any in this example. So the extended Hamiltonian is the same as the total Hamiltonian in this simple example. And now we come to the point where we have a choice. Do we want to leave the gauge freedom intact or remove it? So the first choice is to leave the gauge freedom intact. So what we need to do then is remove or sort of get rid or hide, if you will, the second class constraints by constructing the Dirac bracket. But in this simple example, there are no second class constraints, so there's nothing to do here in step 9. And similarly, in step 10, to reduce the Hamiltonian by using the second class constraints to eliminate some variables, there's nothing to do in this example because there aren't any second class constraints. So basically, we're already done with choice 1 when we constructed the total Hamiltonian. All right, so but we will construct look at choice number 2 in a moment, where we remove the gauge freedom. Before I do that, I want to take a little bit of a diversion because this is an important point, I think, that can be illustrated with this example. So in this simple example, we have the extended Hamiltonian is the same because there are no second class constraints, there's no secondary constraints. The extended Hamiltonian is the same as the total, is the same as the primary. And here it is. I just wrote it again. I had it written down earlier. From this extended Hamiltonian, or primary Hamiltonian, if you will, we can construct what we call an extended action, which is a functional of the Q's and P's, the coordinates and momenta, and the Lagrange multipliers. Okay, and it's just the usual PQ dot minus H. And now from this extended action, here it's written again, we can eliminate the P's using the equations of motion that come from varying the action with respect to P. So this is the usual thing that you can do in Hamiltonian mechanics. You can go back from the Hamiltonian form of the action to the Lagrangian form by just varying the action with respect to the P's, solving the P's, and putting that back into the action, and you get back to the Lagrangian. If we do that here, again, Mathematica is nice. Here are the equations of motion for the P's. Comes from varying this extended action with respect to the P's. And now we can insert these expressions into the action to eliminate the P's. What we get is an action that's a functional of just the Q's, or in this example, Y, and the Lagrange multipliers. Okay, so this is the Lagrangian that you get when you do that in this example. Notice it depends on all the velocities, y1 dot, y2 dot, and so forth. It depends on the y's. There's these potential energy terms. It also depends on the Lagrange multipliers here and here. Okay, so we could go yet one step further and eliminate the Lagrange multipliers using those equations of motion, vary the action with respect to lambda, set it equal to 0, and plug the result back into here. And if we do that, it gives the original Lagrangian we started with in this whole process. But I want to actually examine this form of the action, because it's this form of the action that I would argue is the analog of the Einstein-Hilbert action in or the Einstein-Hilbert Lagrangian in general relativity, or also the Maxwell Lagrangian for E and M. These theories, when you just write down the action in what we usually call Lagrangian form, they actually depend on the Lagrange multipliers. So for general relativity, the quantities, the Lagrangian is a Lagrangian is a function of the metric. And the metric includes sort of the TT components and the TI components, the time-space components. But those are actually, if you examine the action, you'll see that these quantities don't appear with any dots. They don't appear differentiated in time. So these quantities are actually Lagrange multipliers. And you'll notice in this form of the action, lambda appears, but it doesn't appear with any time derivatives. Okay, and likewise for the Maxwell Lagrangian for E and M, the Lagrange multiplier is actually the t component of the vector potential. If you expand out the Lagrangian, you'll see that there are no time derivatives of this quantity appearing anywhere in the Lagrangian. So I think this has caused a lot of confusion over the decades, really, because people were really wanting to understand the Hamiltonian form of say GR and as well as Yang-Mills and electromagnetism, but it's confusing, right? Because the Lagrangian that we're given actually is sort of an intermediate Lagrangian. It already has the Lagrange multipliers in place. All right, so in some sense, you don't want to, if you're studying general relativity or electromagnetism, you don't really want to apply the Dirac-Bergmann algorithm as Dirac described it, because the Lagrangian you're working with is not actually a Lagrangian that's independent of Lagrange multipliers. It already has Lagrange multipliers built in. And you save yourself a lot of work if you just recognize that from the beginning and don't try to mistake these quantities, A sub t and GTT. And so don't try to mistake those for generalized coordinates, but recognize them as Lagrange multipliers from the beginning, and then sort of dive into the middle of the Dirac-Bergmann algorithm to find the conjugate momenta and the Hamiltonian form. Okay, so I want to go back to return back to this example that I've been talking about. This is the extended Hamiltonian. It's the same as the total Hamiltonian. And let's take a look at choice number 2. To eliminate the gauge freedom, we need to impose a gauge condition. And just to let you know briefly, what we're doing here in a sort of geometrical view is the following. We're actually identifying the physical states of the system as curves in phase space. So here's a little picture of phase space as if it were two-dimensional. And each physical state corresponds to a curve. There's one curve with the arrows, okay? So, and the points along these curves differ by a gauge transformation. So these are gauge orbits. And these curves are generated by the gauge generator, this epsilon phi, okay? And when we choose a gauge condition, some condition like, say, chi equals 0, what we're doing is we're selecting out a representative point along each one of these curves to represent the state of the physical system. So, for example, here's chi equals 0. This curve might be chi equal 1. This is chi equal -1. So let's say we have a point in phase space up here. We really want to make sure that we can slide this point along this gauge orbit to get to chi equals 0. And in order to do that, we have to know that the gauge that this gauge condition actually changes when we perform a gauge transformation. So we have the requirement that delta chi, which is the bracket of chi with the gauge generator, has to be non-zero. So this is a requirement for a good gauge condition, is that this quantity is non-zero. That allows us to, no matter where we are, we can always slide the point back to this representative point at chi equals 0. Okay, so in this example, I'm going to choose the gauge condition y1 minus y2 plus y3 minus y4. And you can check that a gauge transformation on this condition is not 0. In fact, it's 4 epsilon. Okay, and together phi, the single primary first class constraint that we have in this theory that generates the gauge freedom, phi and chi together are second class. Okay, I mean, that's just basically this calculation up here without the epsilon, right? So now that we have a system with just second class constraints, we can construct the Dirac bracket. So here's, I call this C all for all of the constraints, the collection of phi and chi. Construct the matrix of brackets, Poisson brackets of the constraints with themselves. This is the Dirac bracket. And again, Mathematica is good at working out all these fundamental Dirac brackets. The non-zero ones I've listed here. There's a bunch of them that are equal. Well, all the Q's with their conjugates are equal to 3/4. The Q's with the conjugate of a different Q is equal to either 1/4 or minus 1/4. And now that we've constructed the Dirac bracket, we can eliminate variables using the constraints. I chose to eliminate P4 and Y4. Again, you could choose to eliminate P3 and Y2. It doesn't matter. You just eliminate 2 of the variables and plug that in to the latest Hamiltonian, which was the extended one. And that gives us a fully reduced Hamiltonian, which for this example looks like this. Hamilton's equations, and these are the equations that I programmed into the Python code to generate that movie. Okay, so this is what Poisson brackets of the coordinates and momenta look like with the fully reduced Hamiltonian. So we could just solve these equations. Once we know these y's and p's as functions of time, we can plug into our expressions here to find y4 and p4, but I chose in my code to do it the other way, which is to go ahead and generate equations for y4 and p4 and evolve those along with the y123 and p123. So you can do it either way. Let's I want to show this one more time perhaps. So you can see, well, for some reason I called the variables x instead of y. But you can see here I'm computing y4, p4 dot, x4 dot, which is really y4 dot. Here, this is where, for the initial conditions, I made sure that the initial data satisfied those constraints. And again, this is y4. Okay, but then I just let it rip, let it evolve forward, and this is just a stupid, simple forward Euler method of evolution. Okay, and this is the result we get with that gauge condition that I just talked about.
Nice.
Okay.
Yeah, this is really pretty cool. Actually now seeing that that the corners could do all totally more or less arbitrary things. At least you can choose 2 and let them do something.
Yeah.
Yeah.
The others are then have to follow, but that's pretty cool.
So what happened to my, what happened to my slideshow? Did I accidentally exit out?
I think I saw a preview, when you,
It's
let
in
things
the
go away.
second
Yeah,
desktop
there, yeah,
at the
yeah, yeah.
top.
Yeah, you can go to the desktop. There you go,
Oh,
yeah.
oh, I accidentally put it up there. Okay. Very good. Thanks. Well, that's really all I have. I just thought as a final slide, I'd throw down a few open questions that I gave about 1 minute of thought to really. That some of the open questions people still think about are the Dirac conjecture. Do all primary constraints generate gauge transformations? One of the questions I have is how do we implement non-canonical gauges? When you'll notice that gauge condition I gave was just a function of the P's and the Q's. But if you look at, for example, the Lorenz gauge in E&M, this is, this index ranges over T, X, Y, and Z. So there's a time derivative here of A0, which is the Lagrange multiplier. So this is not just a restriction on the P's and the Q's. It's actually got time derivatives of Lagrange multipliers in it. So how do we implement a non-canonical gauge like this into the Dirac-Bergmann algorithm? And finally, I think I mentioned last time, one question I've had for a while is how can we construct a Hamilton-Jacobi theory for a constrained Hamiltonian system? And I think there are probably people who feel like they know how to do this. I mean, there's a short section in the Henneaux and Teitelboim book where they talk about Hamilton-Jacobi theory, but I've never really been able to understand it. And for me, at least for me, this is an open question because I'd like to find some argument that I like that resonates with me for how to construct Hamilton-Jacobi theory. All right, thanks everybody. Again, I went on for a long time. You're very patient. Thanks for listening.
Fantastic, thank you. We had some questions during, but do we have further questions now? Ben, please go ahead.
Thanks for the talk. So this Dirac-Bergmann algorithm where you're just modifying the Hamiltonian. Before you modify the Hamiltonian, you just compute the normal Poisson brackets, where you get the wrong equations of motion if you just naively compute those Poisson brackets.
No, you don't get the wrong equations of motion. They're correct, but that's what I tried to emphasize in the last lecture, that I don't know if I did a very good job of it, but it's the equations are fine. It's just that they don't lend themselves to a proper interpretation as an initial value problem. Because, for example, the constraint equation that you get, it has to hold for all time. So that means that you're not free to simply set initial data that satisfies that constraint. Okay, so what I'm talking about here is the primary constraints aren't enough because hidden in those equations of motion, since they come from an action, they hold for all time, hidden in there is that there are further restrictions on initial data that come from the fact that the primary constraint itself has to be preserved under the time evolution. And so by looking at the consistency conditions and generating secondary constraints and so forth, you're just making that explicit. Okay. Another way of saying it is if you look at if you stop at that point where you've computed the primary constraints and Poisson brackets, you can do that. But when you choose initial data, not all initial data that you choose will be consistent with those equations, because some of that initial data you choose, even if it satisfies the constraints initially, it won't satisfy the constraints later. So you have to put further restrictions on the initial data. Okay, again, it's a subtle point that I think I tried to explain last time. No, I'm not sure how successful I was, but it probably takes two sentences in Dirac's, or one sentence in Dirac's book. So
if you constrain the initial data, that's going to be equivalent to the Dirac-Bergmann algorithm. You do either or.
Yes, I mean, because okay, so the only place where you might argue that you've departed from the original Lagrangian system in terms of the physics is when you go to the extended Hamiltonian and you add the secondary and tertiary first class constraints in with Lagrange multipliers. At that point, one could argue that you're describing the system in a different way, or you've actually changed the dynamics of the system. Although, again, in most sensible examples, it seems that it's for a reason, and it's the only thing you've changed is the way you're describing the gauge freedom. So, so apart from that issue of the extended Hamiltonian and the Dirac conjecture, every Hamiltonian, every version of the theory that's been written down is equivalent to each other. So
Maybe
it's
just,
more a matter of just the way you want to think about it and the way you want to interpret it. If you want to interpret the theory as strictly as an initial value problem, that's where you get into these secondary constraints and so forth.
maybe just to follow up on that, what do you mean by it's an equivalent way of viewing the system? And maybe putting words in your mouth, and especially what I mean is, if I think about it, maybe it's just a little bit easier for me to think about it from the Lagrangian perspective. If I have a constrained Lagrangian system, I have these two choices. One where I remove a coordinate. Well, if I have a holonomic constraint, I remove a coordinate, and then I have a different Lagrangian. And when I vary the action, all of my variations are independent. Or I can keep all of my original coordinates, but then I adjoin the Lagrangian with this extra Lagrange multiplier multiplying the constraint. And then when I vary the action, I pretend that all of my variations are free and independent of each other. So that actually seems quite different ways of viewing the same system.
But they have the same dynamics.
Yes, certainly we
Right.
want to make sure that we get the same physics out. Otherwise, it's
Right.
just wrong. It's just wrong, right?
Yes, and that's what I'm saying. You always get the same physics out
Hmm.
in each of these cases.
And that's also true with the extended Hamiltonian, right? You still get the same physics, don't you?
Well, I mean, that's the contentious question. It's in the example that I went through in that paper, yes, you do get the same physics out.
Hmm.
But there are supposed counterexamples that I've never studied in any detail, actually, in which you actually change the physics by going to extended Hamiltonian. But these are contrived examples, right? They're not physical examples to begin with. So it's a little bit hard to say what you mean by physical.
It's sort of terrifying to think that you sort of do this procedure and you don't know when it's going to give you the correct answer or not.
Right. Well, if you think that Mother Nature defines systems by a Lagrangian, then you better make sure your equations are equivalent to the Lagrangian equation. Right.
Sure.
But you may decide, well, Mother Nature prefers Hamiltonians. Maybe Mother Nature defines systems with an extended Hamiltonian.
Hmm.
So I think it's a little bit of your perspective. But I do want to follow up on this. So we went through lots of different steps where we're modifying the Hamiltonian and then the equations are changing and adding this and that. They're all equivalent, like I said, up to the point of doing the extended Hamiltonian, which is a point of contention. But up to that point, they're all equivalent in the sense that you can write down those equations and then you can work your way back just at the level of equations of motion. You can solve for the p's and substitute in those other equations, and you could work your way back and get the original Lagrangian equations. So in those cases, it's clear that you're not changing anything about the physics. I mean, okay, so it's hard to do in general formalism, but like if you take an example like the one I wrote about, you can do that. And that's a lot of what I did in that paper is just to go back and just verify that everything's consistent, the physics hasn't changed.
Great.
Anything else?
Eric?
Wait, so one small question. So often you have like a Poisson bracket of different constraints. I think it was like a phi and a psi, and that was not equal to 0, and that tells you something about your constraints. But I mean, your constraint phi is equal to 0. So if you take the Poisson bracket of something that's 0, you should still get back 0. Right?
You're saying it's independent. Letting it.
Well, just
Yeah,
because
that's
derivatives are 0.
You're calculating derivatives, that's the point.
right. So just because phi is 0 doesn't mean its Poisson bracket with something else will be 0. But the
Zero on the solutions, right? It's zero.
what?
It's 0 on the physical solutions, right? That's the thing. And then you can have derivatives as you try to push it off. Right?
Oh, I see.
Yeah, derivatives push you off of that
Mm-hmm.
0 surface. But the Dirac bracket does have the property that the Dirac bracket of a constraint with anything else vanishes. It's actually constructed that way. So yeah.
So in some sense, the Dirac bracket, if you're on the solution surface, make sure that it doesn't push you off the solution surface.
Yes.
Yeah.
In some sense, it guarantees that you're just still working on that surface. You're not sort of pushing off of it.
Okay, I have 2 questions. One is a little bit vague, but you talked about all of these different methods up to the extended Hamiltonian, always giving you the right answer. And this is a bit vague, but I wonder if you have a sense of why that is, and why I say that is that it just seems kind of miraculous to me that you can get these Lagrange multipliers as a function of the Q's and P's, and it can be some crazy formula. And then when you compute the brackets, it's like horrific things, and exactly like you, I just do it on Mathematica, and it spits out these enormous equations, and it just works. And it feels kind of magical. So there's not really a question. I wonder if you can comment on that.
Yeah, I mean, I think that's part of the fun to me is that it does seem kind of magical. It's because you go through this really long chain of logic and reasoning, and somehow it's right. It all works.
Yeah. And amazing to think that Dirac was doing this back before Mathematica and the ability to numerically solve these horrific systems of equations, and it just worked.
But I think Dirac always worked at the formal level. He didn't actually he doesn't have any examples. But it's really amazing when I think about it that he knew, for me, I learn mostly by examples and I see, oh, this could happen, that could happen. But Dirac just knew what the possibilities were. He could kind of envision it in his mind. And yeah, I mean, honestly, I still have a hard time keeping all these steps straight and so forth and that's why as I mentioned in the first lecture, after first learning this stuff way back in the 80s from Marc and Claudio, I just still was kind of confused, and I wanted to revisit it and try to clarify some of these subtleties and understand it better.
I think it's such an incredible testament to Dirac. But okay. So the last question: have you ever tried to quantize any of these theories?
No, I haven't, and that's really. I mean, somebody brought that up last time. I think that would really be interesting to do. Just take a simple system, and see what happens, because that was the original motivation, right? But I'm not sure how far that original motivation was really carried forward. So yeah, I'm thinking about it. Maybe I find a good student to do that, or
Fantastic.
yeah, I think that's actually a great idea.
Cool. Very good. Well, I think that's a great place to wrap it up. So let's thank our speaker again. Well, again, really appreciate you taking the time, and this was